Welcome back, guys. Today we're going to be reviewing IMO 2024 problem 1. So I solved this problem with Hermitage identity, and it's a really useful function, and it's a really useful tool in number theory and floor functions. So we need to find all real numbers such that for any positive integer n, the following sum is always a multiple of n. So let's make a quick observation for n equals 2. The floor of x plus the floor of x using Hermitage's identity. So we get the floor of n times x is equal to the floor of x plus floor of x plus 1 over n, the all the way to the floor of x plus n minus 1 over m. So we're going to get the floor of x plus 1 over 2 here. And this needs to be divisible by 2. This is divisible by 2, so the floor of x plus 1 over 2 needs to be divisible by 2. Okay. Now, let's just, the first observation, like the first thing I want to say that will be useful later is how many numbers are here. So we have here m numbers, wait, m minus 1 here, total of m numbers. But if we exclude this floor function from x, that's 1 minus 1, so m minus 1 numbers, right? This is useful because I'm going to need it for the solution, and I'm just going to explain this now. And now let's try n equals 3. What will happen? We have 3 times the floor of x by Hermitage's identity, then the plus the floor function of x plus 1 over 2 plus the floor of x plus 1 over 3 plus the floor of x plus 2 over 3. Okay. Now, this is divisible by 3, and from these numbers, what can we say? All three of them they have to be equal to each other, because at least 2 of them are equal to each other. Not all 3 of them are different. At least 2 of them are equal. So let's just say this is k, and if this is k, and this is k plus 1, you have 3k plus 1 needs to be divisible by 3. It's absurd. But like if this is k and this is k plus 1 and this is k plus 1, you get 3k plus 2 is divisible by 3, and that is absurd as well. So the floor function, the fractional part of x will need to be less than 1 over 3, because otherwise these three won't be equal, because x plus 2 over 3 doesn't have to reach 1. It must not reach 1. Now let's just make this clear for like let's just try n equals 4 and let's see what happens there. N equals 4. Well, you get 4 times the floor of x plus this thing right here, we call it s, or let's just say 3k, then plus the floor of x plus 1 over 2, the floor of x plus 1 over 4, x plus 2 over 4, and the floor of x plus 3 over 4. Well, since we know this fact, we know this is k as well, and this is k as well, because the ceiling part of x is less than 1 over 3, right? So we have 4 times the floor of x plus 5k, 5k plus something. Well, that something is either k or k plus 1. This is divisible by 4. This can't be k plus 1 because 6k plus 1 isn't divisible by 4. But 6k is divisible by 4 because here we know that k is even by this right here that we got from n equals 2. So we get that this fractional part of x needs to be less than 1 over 4. And, well, it looks like we're seeing something. For n equals 3, the fractional part of x is less than 1 over 3. then the fractional part of x is less than 1 over 4. So maybe try generalizing for n. So we get the sum, let's call it s, is equal to n times the floor of x plus, well, remember this, since let's just apply strong induction. If we know that if it works for n minus 1, from 1 to n minus 1, if and only if fractional part of x is less than 1 over n minus 1, we will prove that if it also works for n, the fractional part of x will need to be less than 1 over n. Now we prove it. S is equal to n times the floor of x plus, remember this, so for 2, if for m equals 2, we have 1 term. For m equals 3, we have 2 terms. And for m equals n minus 1, we have n minus 2 terms. So we're going to have k times 1 plus 2 plus, because we know all of them are k. We know everything is k other than what I'm going to say here, n minus 2, then plus n minus 2 times, look, we have n terms in Hermitius identity. Minus 1 is the term that I counted here, the floor of x, and another minus 1 is the term that is here, plus n minus 1 over, right? And everything else is k. We have k times 1 plus 2 plus 3. This is divisible by n. And now we look at this. So we have k times n minus 2 times n minus 1 over 2 plus n minus 2, which is equal to k times n minus 2 times n plus 1 over 2, because you have like plus 2 times n. This is easy. Now, this is congruent to negative 2. This is congruent to 1 mod n. And this is congruent, this whole thing is congruent to negative 1 mod n. Because negative 2 divided by 2, that's negative 1 mod n. So the entire thing is congruent to negative k mod n. So the floor of x plus n minus 1 plus n minus 1 over n needs to be congruent to k mod n for this to work. But if we pick n really large, it will surpass k, so this just means that the floor of x plus n minus 1 over n needs to be equal to k. Or in other words, the ceiling function of x will be less than 1 over n. That does it. So we've proved that the part, not the floor function, the fractional part of x needs to be less than 1 over n. Now we proved that for all working n, but according to the question, it will work for any positive integer n. If we pick n, let's just pick n infinitely large, then the fractional part of x will need to be less than 1 over infinity, which is approaching 0. So the fractional part of x will need to be less than 0. It can't be less than 0, but as we increase n, the fractional part needed decreases, which is the same as saying that the fractional part of x needs to be 0, because it needs to be less and less than everything. Like if we pick like 1 over less than 1 over 99, let's just say now 1 over 99, then we pick n equals 100, and it needs to be less than 1 over 100. Then we pick n equals like 10 trillion or something, and it needs to be less than 1 over 10 trillion. We keep increasing n, the fractional part needs to decrease, but the only number that will always be less than 1 over n for any n is just 0. So the fractional part of x needs to be 0, and that just leaves that x is an integer, but it doesn't end there. X is an even integer because x plus 1 over 2 floor needs to be 0. I mean, needs to be divisible by 2. So the answer, x is an even integer. And that's a nice place to stop.